This station is now the ultimate power in the universe.
That may be correct in a galaxy far, far away, but here, stars hold that destructive power too. Let's introduce 3 new systems whose Death Stars are working to destroy their retinue of planets.
Science violation. News flash.
Welcome to another Science Violation with your host, Professor Jenkins. And on today's show I want to discuss a very exciting topic about how stars can destroy planets on short period orbits, those planets that are orbiting very close to the stellar surface. In particular, I want to focus on how we can leverage that destructive power in our quest for uncovering new worlds. And the way I want to do that is to showcase 3 new planetary systems from our team, where one planet, at least in the system, is showing evidence of that destructive power of the star. Now, the project in question is called the Dispersed Matter Planet Project, or DMPP for short, and it was the brainchild of our collaborator, Professor Carol Haswell from the Open University in the UK. And the idea here is that we can hunt for planets that show evidence for losing their atmosphere, for losing their material, their mass, due to this intense radiation from the host star. And the way we can do this as part of this project is to focus our efforts only on stars that show the most depressed levels of stellar activity. That's to say that when compared to the greater population of stars in the galaxy, these stars that we focus on have very, very low levels of activity. They're really, really inactive. Now, this is important because of the way we calculate stellar activity in this sense. We analyse the flux in the core of the calcium H and K spectral lines, and these are the strongest spectral lines in the optical spectrum of Sun-like stars. And the reason we focus on the core is because the core of the line was formed in the chromosphere of these stars. And that's where the effects of stellar activity are most strongly manifest. And therefore, if we can witness stars that have very, very deep calcium H and K lines compared to the population of their brethren in the galaxy, then we can hypothesize that potentially there's a planet orbiting around the star that has a cloud of material, a cloud of calcium gas that's also absorbing the photons from the star. And that's what gives rise to this very depressed calcium H and K line core. And then we can go to the telescope and observe those stars using radial velocities to hunt for the signatures of orbiting planets. And I encourage you to check out the lightning class on this channel on radial velocities to gain a better understanding of what those measurements entail. And if we detect a planet on a very short period orbit around the star orbiting close to the stellar surface, then we gain confidence that our model, our hypothesis is correct. That we have a planet that's orbiting the star where material is being ablated from the world as it's going around its orbit due to the intense irradiation from the star. And that ablated material is absorbing, is blocking some of the light from the star, such that the star itself appears to be very, very inactive when we look at those calcium H and K lines. Now, for that to be the case, this material must form a ring all the way around the star following the planet's orbit. It's being ablated from the planet, so it's constantly being replenished, and it must contain high amounts of calcium. And that's why we see the depression in the calcium H and K lines, because that calcium in the torus, in the ring, is absorbing photons at the correct energies such that we get this really deep calcium H and K line that makes it look like the star is very inactive. Okay, so I promised you 3 new planetary systems. Let's start with DMPP1. Now, this star is located at a distance of around 200 light years from the Earth, and it's a little larger, a little more massive than the Sun. It has a mass of around 1.2 solar masses, and it's about 1.6 times larger than the Sun, and its spectral type is classed as F8V. Now, not only is this star orbited by one planet that we know of, but it's orbited by at least 4. The planetary system is quite diverse. There's 3 inner planets on very short period orbits. Those orbits are about 2 days, 3 days and 6 days. And then there's an outer planet that orbits with a period of about 20 days. The inner 3 planets have masses ranging from 2 to 5 Earth masses. and the outer planet has a mass of around 20 Earth masses. Now that means that the inner planets are what we call super-Earths. They're things a little larger than the Earth, a little more massive. And the outer planet is likely something like Neptune. It's more like a Neptune-type planet. Now, we have to remember that these masses are minimum masses, and that's all we get from the radial-velocity measurements alone. And so we have to keep that in mind, that these are minimum masses. But we believe these masses are close to the absolute masses of the planets because we see the presence of that shroud of material. That means that the inclination of the planetary system to our line of sight has to be close to 90 degrees. It has to be close to edge on. Even more interestingly in this case are the range of temperatures we find for the planets. The temperatures range from around 600 degrees to 1500 degrees Celsius. And at those upper temperature ranges, 1500 degrees or so, it's hot enough not only to ablate the planet's atmosphere, but if there is no planetary atmosphere, it may be hot enough to evaporate the surface rock. That means that the rocky surface of the planet may be ablating and adding its material to the ring of material around the star. And therefore, if we can follow up that ring and we can study the chemicals of that ring, then we can understand the chemistry of the planet's surface. And for the first time, we can then study exoplanet surfaces. The next system, DMPP2, is located at a distance around twice that of DMPP1, about 440 light years from the Earth or so. And it's also a more massive star. It has a mass about 1.5 times that of the Sun, and it's about twice as large almost. And the star itself is classed as an F5V star. In this case, the star is only orbited by one planet that we know of, and it's also a system that's very different from DMPP1. The planet has a mass of around half that of Jupiter, and it orbits the star with a period of around 5 days. That means it's much more massive than anything we found around DMPP1, and it's in this special class of planets called hot Jupiters. Now, hot Jupiters are broadly classed as gas giants that orbit within around 10-day orbital periods or so of their star, and they're a class that only are found around, say, 1% or so of stars that we observe. Interestingly, the star is a type of star called a Gamma Doradus pulsator. That means the star is kind of ringing like a bell, and that caused a lot of problems to actually detect this planet. The radial velocity measurements are heavily affected by that pulsation noise, and so to pull out the signal of the planet requires a lot of specialised techniques to mitigate that noise of the pulsating star. Finally, we come to the DMPP3 system. And DMPP3 is located at a distance of around 160 light years from the Earth, and it's also slightly smaller than the Sun. It has a mass and physical size around 0.9 times that of the Sun, and it's also a slightly cooler star. It's a spectrotype K0V. Now, one of the interesting things about DMPP3 is that it's not a single star. We actually found it has a binary companion, DMPP3b. The planet, which orbits the primary star in this system, is another of these hot super-Earths. It has an orbital period of 6 days and a mass between 2 to 3 Earth masses, and that gives the planet a temperature of around 580 degrees Celsius. Now, at this temperature, it's not hot enough to evaporate the rocky surface, but if there's a gaseous atmosphere, we do believe that it's hot enough to ablate that planetary atmosphere, and that could be providing the donut or the torus ring of material that blocks out the calcium H and K lines, that gives us that depressed calcium HK feature. And so this is another of these systems where if we can follow up that material, that ring of material, and we can study chemically that ring of material, we can gain an insight into the small planet's atmosphere. It's humbling to think that we can look up into the night sky with wonder and point to stars that we know have planetary systems, and we know the conditions of those planetary systems, extremities much more violent than what we experience in the solar system. And not only that, but those violent interactions, those stars that are trying to destroy their retinue of planets, are giving up their secrets to us earthbound astronomers. And with that, I'll say, remember, it only takes you to ask the right question to change the course of history.
Science Violation.